In August 2008, the sky over Beijing was remarkably clear for the opening ceremony of the Olympic Games. This was not meteorological luck. The Chinese government fired thousands of rockets into the sky to force approaching storm systems to drop their rain before they reached the stadium. Humans have been trying to command the skies for decades. During the Vietnam War, the United States military ran a classified program called Operation Popeye. The objective was to artificially extend the monsoon season, flooding the Ho Chi Minh Trail to create enough mud to halt enemy supply lines. Because of stories like these, it is easy to imagine that we possess a weather machine, that scientists can simply point a laser at a clear blue sky and conjure a thunderstorm out of thin air. But the reality is strictly constrained by atmospheric conditions. You cannot seed a dry sky. Weather modification is entirely dependent on pre-existing moisture-laden clouds. We don't create the water. We hack the physical processes inside the cloud to force it out. To understand how we force a cloud to rain, we have to look at how clouds operate naturally. Clouds are essentially massive collections of water vapor. But that vapor can't turn into liquid water on its own. It needs a microscopic surface to cling to, usually a speck of dust, pollen, or sea salt floating in the atmosphere. This is where nature often encounters a bottleneck. If a cloud lacks a high enough concentration of these floating particles, the water droplets that do form remain too light. They stay suspended, bouncing around in atmospheric updrafts, never gaining the mass required to fall to the earth. Meteorologists call these tiny surfaces cloud condensation nuclei, or CCNs. Think of them as magnetic cores for moisture. When vapor collides with a CCN, it condenses into a tiny droplet. When a stubborn cloud holds on to its moisture, it is starving for these nuclei. To trigger precipitation, scientists bypass this natural shortage by injecting millions of microscopic cores directly into the storm, forcing the physical reaction to complete. Today, the primary delivery system for these artificial cores is a specialized aircraft. Pilots fly directly into target clouds, igniting ejectable pyrotechnic flares mounted on the wings or the belly of the plane. The delivery method used to be far more makeshift. In 1952, Indian scientist Dr. S.K. Banerjee achieved the country's first artificial rainfall by sending chemical payloads up into the clouds using simple hydrogen-filled balloons. Whether by balloon or by modern aircraft, the payload depends entirely on the temperature of the cloud. For warm clouds, meteorologists use a technique called hygroscopic seeding. The execution requires precise flying. The aircraft targets a 40-kilometer wide area, flying in a continuous loop back and forth through the middle of the cloud. Crucially, they must deploy the payload right inside the cloud's updraft region. The flares burn through roughly 1 kilogram of sodium chloride, ordinary table salt. This disperses an incredibly fine mist of particles, calibrated to a uniform size of 0.5 micrometers. The goal is a concentration of 1 to 10 salt particles per liter of cloud air. Ambient vapor immediately latches onto these highly attractive salt particles. The droplets quickly collide, coalesce, and rapidly increase in mass. Those natural updrafts that were keeping the clouds suspended now work to circulate the heavy salt droplets. Hygroscopic seeding effectively turns a warm cloud's natural airflow into a highly efficient localized rain factory. If the storm is higher in the atmosphere, temperatures drop anywhere from -7 to -20 degrees Celsius. These are known as supercooled clouds, and they require a completely different approach: glaciogenic seeding. At these sub-zero temperatures, liquid water still struggles to freeze because there is a severe deficiency of natural ice nuclei. To fix this, scientists inject materials that mimic the geometric crystalline shape of ice, like silver iodide or solid carbon dioxide, better known as dry ice. The physical reaction to dry ice is immediate. As a single 1-centimeter pellet of solid carbon dioxide falls through the cloud, it flash cools a thin streak of the surrounding air. That localized drop in temperature causes spontaneous ice formation. A single dry ice pellet generates roughly 1 million microscopic ice nuclei in its wake, setting off a chain reaction as the cloud's updrafts and downdrafts violently circulate the new ice crystals. The effect on the cloud structure is drastic. During early cloud seeding experiments in the 1940s, scientists captured aerial photographs showing perfectly circular holes punched straight through thick cloud layers, entirely cleared out by the seeding agents. Unlike warm cloud seeding, which simply gathers liquid water together, glaciogenic seeding causes the supercooled droplets to freeze, collide, and shatter. These broken pieces serve as larger embryos, accumulating more moisture until they fall as snow or heavy rain. This chart shows the measured, long-term global efficacy of these operations. When deployed consistently over long periods, cloud seeding programs produce an estimated 10 to 15% increase in natural rainfall and snowfall compared to baseline levels. However, despite 75 years of active practice, the science remains heavily debated. While long-term averages show clear bumps in precipitation, the results of any single short-term seeding mission remain highly unpredictable. The entire process is bound by the strict constraints of atmospheric chemistry. If a region doesn't have the exact required moisture levels, specific temperature bands, and cooperative wind conditions, the chemical reactions will fail to produce a single drop of water. Cloud seeding is not a magical weather machine that allows us to command the sky on a whim. It is a highly precise feat of atmospheric chemistry, one that simply gives nature a microscopic nudge to finish what it already started.